Another enhancement that we can look at is an enhancement that we previously used for dynamic programming, for value iteration, and that is to try to prioritize the different, our experience, the different state and action pairs that we've seen previously, when we consider which one of those should we update, or for which one of those are we going to simulate new transitions for. And the question is, do we actually have such priorities, or do some SA pairs matter more than others? And we actually we've seen that before, right? We've seen that in prioritizing sweeping in dynamic programming, and we can do the same here. So for instance, let's look at these two transitions. Transition number one is from state X to state Y to state Y. Currently, state X has a Q value approximation of 10, and state Y has a Q value approximation also of 10, and the immediate reward is approximated at 1. And we have another transitions between state Z with a Q value of 0 to state W with a Q value currently of 10 and an immediate reward of 1. So the question is, which of these should have a higher priority? X right or Z right?
Z right.
Why?
Because you're updating its Q value by a larger amount.
It has a larger TD error, right? Yes. So if we're going to update the state, or we expect to update it by a higher value, that is, it has a higher TD error, then that is how it's a simple heuristic for setting the priority. Right, and indeed this is another enhancement that we can perform. We can prioritize updates according to the TD error. As a reminder, the TD errors follow from the online Bellman equation. Or actually from the Bellman equation, but for what we're doing, in the online case, we can replace this Bellman equation with the online Bellman equation. So let's now try to compute the priorities for both transition, X right and Z right. So for X right, we can see that the TD error in X is 1, right? So the current Q estimation is 10, and the immediate reward plus the estimation in the next step is 11, so the TD error is 1, and we can do a similar computation for the next transition, from Z going right to W, and we can see that the TD error there is 11. And so now we can define a prioritized sweeping version of DynaQ, right? And here, for each transition that we observe in the environment, we add it into a replay buffer. A replay buffer is just a large buffer with all of the transitions, or many of the transitions that we've seen so far. But now it's a priority replay buffer. So each transition also is given a specific priority. That is based on the TD error, okay? And then when we repeat n times, that is when we do Q value updates that are repeated n times per real world transitions, we first of all pick the first transition in our priority queue, in our priority buffer, and we do a Q update based on that transition. And then, once that S was updated, the one with the highest priority, we check if and by how much all predecessor states need to be updated, their priority, right? And we insert relevant transitions to the replay buffer with the relevant priority. So this is very similar to what we've seen previously in the value iteration case, the prioritized sweeping value iteration. So let's see how this would work in our toy example. So again, we're looking at the same toy example as before, for connected grid with different resolutions. I'll show you now results for different resolutions I'm showing you now results for these different resolutions. What does it mean? So here you can see the lowest level resolution. This is the grid with the lowest level resolution, but then we can also divide each one of the cells into 4 cells or into 9 cells and so on, and make this a much larger state space, right? Much higher resolutions. And of course, in that case, the episode leading to the goal is now much longer. As before, we have deterministic action outcomes, +1 reward for moving into state G, 0 otherwise. We have a discount factor of 0.95 below 1, that is, the optimal policy should get to the goal as soon as possible. Hyperparameters are as before, but now we have a set n, and we set to a value of 5. It's always the value of 5. And the results here on the right shows you the number of updates that were needed until we uncovered the optimal solution, the optimal policy. And of course, lower is better. Again, this is a log scale, so the difference here is much larger than the same difference here. Okay. Common log scale. And the x-axis here is the grid world size. So larger grids, of course, requires more updates until we find the optimal solutions. But as we expect, I mean, hopefully you expect that, as the grid size grows, the state space grows, prioritized sweeping is more effective because propagating the values locally becomes more meaningful. So we propagate them in the correct order, that is, we start from the goal and propagate the value backwards through the state space instead of propagating the value one step at a time, right? This is specifically important in sparse reward domains, where propagating the reward value or the Q values throughout the state space is very slow, and prioritized sweeping can help a lot with that. And indeed, you see here that DynaQ is much slower compared to using prioritized sweeping. And this difference between the performance becomes much larger as the size of the grid world of the state space increases.